Here we go again with two more. We have 61 and 65. So for 61, it's sine x minus cosine of x minus 1 equals 0. So this is going to be the kind that we should check our solutions because guess what's going to happen? Any guesses? Yeah. When we're relating to sine and cosine, the relationship we have is that Pythagorean identity. And the only way to really get that across is to substitute the square root. So if I were to add cosine of x to both sides, that's sine of x minus 1 equals cosine of x. This is where the square root's going to come in. So just recall that sine squared x plus cosine squared x equals 1. So cosine squared x equals 1 minus sine squared x. So cosine of x would be the square root of 1 minus sine squared x. A little sloppy there. So this goes in place of the cosine, and it gets everything in terms of sine. So that sine of x minus 1 equals the square root of 1 minus sine squared x. And you guessed it, the next step is to square both sides, thus introducing the potential for extraneous solutions. So we have sine squared x minus 2 sine x plus 1 equals 1 minus sine squared x. So now if I were to subtract 1 from each side and add sine squared x to both sides, we would have 2 sine squared x minus 2 sine x equals 0. And from here, I can factor out a 2 sine x, and I have sine x minus 1. So 2 sine x equals 0. So x would be, let's see, 0 and pi. And let me see what the instructions say. Can we do a 2 pi, or do they close it off? Is it open interval there? And they say not doing a 2 pi. And then sine x minus 1 equals 0. So sine x equals 1. So x would be pi over 2. But let's check these results and see if they work in the original. In the original, we had sine x minus cosine of x minus 1 equals 0. So sine of 0 minus cosine of 0 minus 1, is that 0? Sine of 0 is 0. Cosine of 0 is 1. So 0 minus 1 minus 1, is that 0? And the answer is no. Sine of pi minus cosine of pi minus 1, is that 0? So that's 0 minus a negative 1, because cosine of pi is negative 1. Minus 1 equals 0. So here it's 1 minus 1 is 0, so that works. So pi works. And then we had pi over 2 as another solution, potential solution. So sine of pi over 2 minus cosine of pi over 2 minus 1, is that 0? So this is 1 minus 0 minus 1. Yep, that works. Okay. So our solutions are x equals pi over 2 and pi. And the other one from this pair is 65. So 65 says cosecant squared x minus 2 cotangent x equals 0. So again, this relates back to the Pythagorean identities. And so if you don't see this, I really encourage you to go back and study, memorize the Pythagorean identities, just to get really familiar with all the identities, because they relate these. The cosecant squared x equals cotangent squared x plus 1. So we immediately substitute this cotangent squared x plus 1 in place of this cosecant squared x. And now we have everything in terms of a single trig function, which is our goal. So we have cotangent squared x plus 1 minus 2 cotangent x equals 0. So cotangent squared x minus 2 cotangent squared x, or 2 cotangent x, not squared, plus 1 equals 0. So this is cotangent x plus, or it's minus 1. I guess I'll do a u substitution. I mean, I can see where this is going, but I probably should help people to see this better. If I said u equals cotangent x, then it's u squared minus 2u plus 1 equals 0. So now you're saying, oh, I see it. That makes sense. That's a u minus 1 squared. That's a, that's a perfect square trinomial. So u minus 1 equals 0, u equals 1. And what was u? Cotangent of x. So where does this happen? This happens in the first quadrant at pi over 4, and the third quadrant, 5 pi over 4. So I'm not checking these because I didn't do anything that's going to introduce extraneous solutions, but you can check this. I mean, it's probably not a bad idea to check these answers. So hope that helps.